Alright, hi everyone. So I'm back with another video in the series of tree-based methods, and this time we are going to discuss uh, a quick overview of what is XGBoost and how does it work, and we are going to implement a vanilla version of it. So basically, XGBoost is a much optimized and efficient version of training tree-based gradient boost trees, uh, which includes many more optimizations, improvements over gradient boosting decision trees. Uh, so one of the most basic concept here is that in gradient boosting trees, we optimize the loss function. So as per the entire series, I'm still talking about the regression problem. So for regression problem, it is a scaled version of MSE, that is a loss function in both methods. In gradient boosting decision trees, we use first derivatives, only gradients, to optimize the loss function. Whereas in XGBoost, we are going to optimize it using both first and second derivatives. So if you see here, this is what our loss function looks like. And yeah, this is a regularized loss function here, wherein this part, the first part, is the scaled version of mean squared error. Y hat and yi, you will calculate mean square between these two values, and whereas this second function is the regularization term. If you see the definition of it, it computes lambda w square. W is nothing but output value of any leaf node in the tree. So this lambda and gamma parameters together, they regularize the loss function. So any one of these, if they are even zero, doesn't mean the regularization will go to zero. Still, we can count on the regularization happening in this case. So how does it work is, initially we start similar to gradient boost. We start with the initial prediction. It can be anything by default for our case, or for our case it won't be 0.5, it will be average of all the values of the target. Then step 2 is we start fitting the XGBoost tree to the residuals. Now this XGBoost tree is something different to vanilla decision trees. Uh, how is it different is, we start with a tree with a single leaf where all the residuals go to that leaf. So let's say our training data has 4 examples, and after predicting the initial value with the average of all the targets, we found that our residuals are these 4. So we start with a tree with single leaf, and the leaf will contain all 4 values. Now next step is we compute output value of the leaf and the similarity score for the residuals. So these formulas might look complicated, but they are derived after optimizing this loss function. So when you I'm not going into the mathematics of it, but there's a very nice video by StatQuest channel uh, defining deriving the output value and the similarity scores out of this loss function. So when you um, approximate this function with first and second derivatives and then solve for it, it ends up to these equations of output value and the similarity score. So basically, output value comes out to be sum of residuals divided by number of residuals plus lambda. Lambda is a regularization term. Now, first it comes out to be negative of summation of all the gradients, where gradients will turn out to be nothing but um negative of the residuals, negative of all the residuals, and Hessian, which is the second order derivative of that loss function, comes out to be 1. So these are not under the scope which I am going through right now, so I'll just skip through it. So output value will come out to be sum of residuals divided by number of residuals plus lambda, and similarity score for each node, each leaf basically, will come out to be sum of residuals squared and number of residuals plus lambda. So once you calculate similarity score for any leaf, we'll have to see. Let us call that root similarity. Next is we'll have to see if we can do a better job clustering similar residuals if we split them into groups. So basically the residuals that are existing here, if we split them into two groups of similar residuals, can we do a better job at splitting them? So how do we evaluate if we are doing a better job or not? We'll need to find a threshold for for a particular feature. So now this can be the data with multi features data set or a single feature. So depending upon that case, we'll have to find all the threshold for a particular feature and for all features, and then we'll have to calculate the I'll come to the gain, but we'll have to compute a number which will evaluate if which threshold and feature we should select to split on, right? So how do we do it? We calculate left similarity and right similarity for each of these combinations, feature and their thresholds, um, for the residuals, and then we calculate a gain. Gain is nothing but summation of left and right similarities, and we subtract the root similarity out of it. So uh, we calculate gain for all thresholds, then the one with the highest gain is chosen to split. So the threshold and feature that gives us the highest gain, we choose that to split first. Higher gain means better at splitting the residuals into clusters of similar values, because when the residuals are quite different in any leaf node, the similarity score will be low, because the sum of residuals will drop down if they are quite different, negative, positive, etc. And when residuals are quite similar in sign or in magnitude, sign and in magnitude, then it can go pretty high. So higher the gain means we are doing a better job at splitting. So yeah, if a stopping condition would be if any leaf has number of residuals that is more than minimum samples split, we again calculate gains for all threshold and features, and then choose highest gain to split for next branch. We continue doing this until we reach a stopping condition, unless we have maximum depth limit reached or number of residuals get less than minimum samples split, so on. Once you have done that, we use a gamma parameter. So in this uh, gamma basically is if you look at the, so let me show you the paper of this particular algorithm. Yeah. So this is the loss function that I showed there. Yeah, so look at this equation number 7. After you have calculated gain at any node, and you choose left or right as splits out of it, and then calculate gains for those left and right leaves as well. This is the formula that comes out for the final gain, which is gain of uh, similarity score of left plus similarity score of right minus similarity score of the root. So if you see, this formula looks quite similar to what we had in the um, first slide of my presentation. But yeah, so this is the gain, and you are subtracting a number gamma. Gamma is a parameter that can help us decide if we are getting a gain above this number, this particular threshold. Let's say it is 100. So if I'm getting gain above 100, only then I'll I'll split that node on that particular feature or threshold basically. If I'm always getting a gain, uh, basically this entire expression is coming out greater than 0, only then we are performing the split. If it is always negative, we are not performing the split. that's what uh, yes. So that's why gain minus gamma is greater than 0 we want. So gain should be greater than gamma. Uh, Now there is another parameter lambda if you see in the regularization component of the loss. This is a regularization parameter, but even if it is 0 or even if gamma is 0 doesn't mean that regularization won't happen. Another lambda or gamma, if only one of those is 0, other can still help us regularize the tree formation, building of trees. When gamma is greater than 0, it reduces the say of any particular residual in that leaf's output value. So when we are calculating the output values, right, there is a factor added in the denominator gamma. So if, sorry, lambda, if lambda is more than 0, greater than 0, the say that this particular this particular leaf would have will reduce in the entirety. So yeah, now so this whatever I showed till now is conceptually the improvements over gradient boost decision trees that XGBoost provides, but there are a lot of more performance related optimization and improvements that XGBoost provides, I've listed here from the paper, but I'm not going to work on the implementation of those. So we are going to implement basic mathematical uh, modeling of whatever is happening at the XGBoost trees level. These things are much more complicated and can be done as exercises. One thing I want to say is this weighted quantile sketch, when we for in our code, when we are going to do the finding best split of feature and thresholds, we are looking at each of the thresholds of the features, which is not maybe not very efficient for big data sets, but looking at the quantiles of the data to find the splits, that is much more efficient. That gives you much less work to do. Okay, so let's do the code implementation now. I have defined a skeleton class here with all the class attributes that would be needed. So you need n estimators, learning rate, max depth, and samples, split, etc., gamma, lambda, all these things would be needed to build a tree. These many trees we are going to build. Init value we are going to define, and this will be a list containing all the trees. So first let's start with fit. So it's more or less very similar to start with as compared to a gradient boosting thing. So we'll first define ypred, which is similar to y, and its values would be filled with self dot init value is equals to np dot mean of y. We fill it with self dot init value. D type is np dot 64. So we have predictions done, initial predictions. Now we iterate over number of the trees that we want. For each iteration, we'll need to first calculate uh, residuals. Residuals will be basically okay. So we'll need to calculate grad, which is we'll define a helper function, gradient of, let's say, y and y pred s equals Hessian is So dot underscore Hessian of y and y pred. So once we have these two things, we'll initialize a tree, which is nothing but XGBoost tree, which we are going to define later. XGBoost tree will pass all these parameters here. Let's get into these parameters later. Then we'll do tree. We'll fit this tree with this data. We'll provide grad and hess, and if also needed y. Then we'll calculate update by predicting from this tree, and we'll update y pred running rate into update, and also then trees dot append. Yeah, so where we have will this is the way we'll create our trees, and we'll update it to the list. Let's say we can also print loss. So that, okay, before we go ahead with anything, we'll have to calculate, we'll have to define gradient function. So gradient is basically negative of minus y underscore pred. So from the presentation, if you remember, gradient is, let me quickly show it once again. So if you look at these equations, derivation we are not going into, the gradient is nothing but a negative of the residuals, and Hessian is 1. So going back to the code, this would be the this should be the gradient, and so it's a vector of all the ones. Oh, sorry, this doesn't have to be this way. You can just say there's ones like y. Yeah, so we'll output this. So this fit method of this regressor is defined. We'll have to define the class of the XGBoost tree, that we'll get to in a second. So to start this prediction, we'll first need to initialize y pred equals to np dot full like x dot shape 0, this should be the shape of it, fill with self dot init value, and the type is np dot float 64. Once we have defined, once we have initialized predictions, then for tree in self dot trees, tree dot predict x, this will be the update. We'll be multiplying this with so this should give us updated vibrate, and at the return we'll return at the end we'll return y predictions. So that should be enough for our regressor class. But before using this, we'll need to define the XGBoost tree class, right? So again here we'll have self dot max depth, self dot in samples split, self dot learning rate we do not need here, self dot gamma, self dot regularization lambda. This will return a tree, and this, and yeah, that's it. So for this fit function in this tree, we need gradient and Hessian. Y may be optional because what happens here is all right. So here we would because we are going to recursively build a tree, we'll need a helper function. So we'll just called dot build tree. We'll pass x grad and s to it. Default depth is 0. I think we would not need this y, but we'll get back to it later. Let's see. Okay, so first here in this, what we need to do is we need to define a stopping criteria, a stopping condition. Then we'll need to find best split feature and threshold. Then after that, what you need to do is you need to uh, update best gains or the outputs. Best gains recursively call build tree for left and right nodes, and then return tree structure, which we are going to be doing in a dictionary fashion. So stopping condition: if depth is greater than self dot max depth, or length of grad or anything is uh, less than self dot min samples split, if either of these things happen, we'll have to update the output. Update the output for the leaf node, because if we are stopping, then that means we have reached a leaf node. So we are calling it as weight, because in the paper you see it is called as weight, or we can also call it as output, whatever it is. So we'll need to do minus np dot sum of grad divided by plus this entire thing is the this entire thing is the denominator. Return, we'll mark this as leaf node with this identifier, and the output as weight. So whenever in our prediction we leave our data sample reach at this particular node, it will predict this weight. So this was our stopping condition. Now we need to initialize a few parameters: best gain, best split, best threshold. Let's unpack the dimensions of this x. Best gain will start with infinity. Now, once we are done with this, we'll start iterating over each threshold for feature and range and features. Threshold np dot unique each row in that column. In that column, particular feature. Yes. So if you remember in our vanilla decision tree implementation, we found out thresholds quite a bit differently. So those both are an okay approach that is maybe more efficient. Okay, sorry, I had to take a break. But yeah, let's continue. So once we have found our threshold, we can, for that particular feature, we can find left mask and right mask. So both this would be a vector of length of number of samples in X, and each values will have true or false depending upon this condition. Once we have this, we need to find if left mask dot sum equals to 0, or if there are 0 elements, if everything is false in left or everything is false in right. Then we don't return, basically we continue, we get to next threshold or next feature. If not, then we'll calculate gain self dot compute gain, and here we have to provide gradient s left mask right mask. Once we have gain, we see if gain is more than best gain. Okay, we should initialize with this with minus infinity. If gain is more than best gain equals to gain, and best split is equals to, we give feature threshold left mask right mask. Threshold feature. So this is the best split. Once we have found the best split, so once we have found the best split, we will check if best gain is less than self dot gamma. So that is the same condition that I showed you in the paper, or best split is none. There is no best split found. In both these cases, we'll have to we'll have to not split and return the leaf node. So we'll have to return something like this, as we did earlier, and output and wait. But wait, as again it would be same as the weight that we calculated here, right? Foot of the leaf. Now we left subtree equals to build tree. So because we are not using y anywhere over here, we can just remove y from this. X grad has depth plus 1. So we'll send it x left mask or rather best splits left mask. Let's copy this. Grad of this, s of this, and depth plus 1. And we'll also recursively call build tree function for this. So this will give us return left and right subtree for us. Once we have returned, now we'll return basically the node, which is feature threshold leaf left subtree best splits threshold best split feature. So this would be the structure of the node that our function returns. Alright, so once we have this, let's now we'll have to define compute gain left we'll have to calculate gain right we'll have to calculate Hessian for left we'll have to calculate, Hessian for right we'll have to calculate. So gain for left will be grad left mask and np dot sum. So this is how we would calculate gain and Hessian for left and right splits. Now total gain, final gain would be nothing but left plus right minus so basically it will be similarity for left would be divide by self dot regularization lambda, this plus this minus left plus right gains similarity is minus similarity of the node. Similarity of the node would be GNL. Alright, so this will be the gain that this function will return, and once we have the gain here, we'll compare it with the best gain. If best gain is less than self dot gamma, we'll not split and we'll return the leaf, otherwise we'll continue splitting. Alright, so then we'll have predict function to end with we are calling a traverse function, helper function, to traverse the tree using this node. Nothing but and the tree will be nothing but something that's not tree is equal to this. So we call loop this over this thing for each examples, and this will give us a column vector, a row vector of size number of samples, right? And for each trees, for 10 trees, we will stack them together. If node is true, return output. Otherwise, if node features less than equals to if value of that example for that particular feature is less than equals to node threshold dot traverse node. So this will recursively um, traverse each nodes, and once it has found the leaf value, the leaf indexes index is true, it will return the output value there. So yeah, this is mostly ready now. Only one thing is left with max depth equals to self dot max depth min samples split equals to self dot min samples split equals to self dot gamma self dot relation lambda. This will initialize our tree. We have this. We can now just XGB model equals to XGBoost regressor and estimators equals to 50 learning rate is 0.01 1e minus 2 max depth equals to let's say 10. Remaining things, let us leave it like this. XGB dot fit 1000 samples oh, sorry. Alright, so I fixed all the errors, and now you can see the this is I'm just training very naively, training a model very naively with 200 estimators, learning rate 0.1 and 10 max depth only for 1000 samples, and I can see that the training RMSLE is going down and down. It doesn't even stop. So yeah, it's probably overfitting or whatever. You'll have to, but yeah, this is not a right way. Instead of training RMSLE, I should have included validation data here, the fit and printed validation RMSLE. So I'll try to do that and push this code on the GitHub and then post it. But yeah, so this is a XGBoost implementation, very vanilla one. Basic conceptually you can understand, but most of the optimizations are not here. Um, they are into parallel training or uh, parallel split finding. There are multiple kind of optimizations. So yeah, um, those are out of scope. Thank you for tuning into the video, and see you in the next one. Bye bye.